This is G485 Homework Booklet, question 28. So starting with the definition, state Hubble's law. The speed of recession of a galaxy is proportional to its distance from Earth. The mark scheme did underline the word galaxy, so that is important to include. Next, the dark lines of the spectrum observed from a distant galaxy are redshifted by 15% of their normal wavelengths. You are given the Hubble constant as 65 kilometers per second per megaparsec. You're also given the conversion from parsecs to meters. Show that the speed of the galaxy is 4.5 times 10 to the 7 meters per second. So you need to use the equation for Doppler shift. Or redshift, we have the change in wavelength divided by the original wavelength is equal to the ratio of the speed of the galaxy to the speed of light. Rearranging that equation, we can put V as the subject. Then the 0.15 corresponds to the 15%, comparing the change with the original wavelength, and we just multiply by the speed of light to give the required answer. Next, you're asked to estimate the distance of the galaxy from Earth. Now this equation is Hubble's law in equation form. So the speed of the recession is here and the distance from Earth is here and Hubble's constant. So rearranging, we want to say the distance is the speed divided by the Hubble constant. So the speed of the galaxy was given and you calculated it in the previous answer, so that is here. And then the remaining part of this calculation is just dividing by Hubble constant. The reason why we have two numbers is to do with the conversion and handling of the units. So if you look back at the question, you were given kilometers per second per megaparsec. Now that isn't consistent with what we need in order to get a final answer of meters here. So we need to convert both the kilometers and the parsecs into meters so everything is consistent. So that conversion is done here in the next part of the question as well. So we have the 65, the value we were given, and kilometers per second on the top line is converted to meters per second by multiplying by 10 to the 3. Now, this constant is kilometers per second per megaparsec. So you can think of the megaparsecs as being on the bottom line of this equation. So you then have to convert the per megaparsecs to per meter. So on the bottom line, we multiply by 3.1 times 10 to the power 22. The 10 to the 22 is simply 10 to the 16 multiplied by 10 to the 6 because of the mega. So those are the figures that we have here in the part above, but because we were dividing by Hubble constant, they are the other way up. So that leads us to the answer of 2.15 times 10 to the 25 meters. Next, estimate the age of the universe in years. So having already found the Hubble constant in seconds, we can say the age is a reciprocal of the Hubble constant. This gives us a value in seconds, and now we need to convert that to years. So you simply divide 4.77 times 10 to the 17 by 3.2 times 10 to the 7, giving an answer of 1.49 times 10 to the 10 years. Finally, once again, we have a descriptive part of the question. The age of the universe is calculated from the time of the Big Bang. Describe two observations that directly support the idea of the Big Bang. There are 2 marks allocated here, and you only need 2 of the following 5 allowed answers. So first of all, spectra from galaxies show a shift to longer wavelengths. Just saying redshift would not have been enough here. Secondly, more distant galaxies are observed to be moving faster. Thirdly, you could point out the existence of cosmic microwave background radiation. The word microwave is important here. Alternatively, you might say that this corresponds to the universe having an average temperature of 3 Kelvin, or that gamma rays emitted during the time of the Big Bang have become microwaves as the universe has expanded and cooled. The fourth possible point refers to the existence of primordial helium. This word simply means that the helium was produced in the early stages of the universe. We find that we can make these observations because when we look at very distant galaxies, we are in effect looking back in time. The final allowed marking point refers to temperature fluctuations in the universe. This also corresponds to variations in the intensity of microwave background radiation.